In this video, we are going to be looking at acceleration, which is defined as the rate at which velocity changes over time, or to put it more simply, it describes how quickly something either speeds up or slows down. There are two fundamental equations that are essential to understand acceleration properly, but we are going to begin with the first and most straightforward one. On the left side of the equation, we have acceleration, which is measured in meters per second squared. On the bottom right, we see time measured in seconds, and on the top right is the change in velocity. If you are unfamiliar with it, the small triangle symbol often used is called the delta symbol, and it simply stands for the word change. Therefore, delta V refers to the change in velocity. In some cases, you might see delta V written in the form of V minus U, where the letter V represents the final velocity and the letter U stands for the initial velocity. By subtracting the initial velocity from the final velocity, we are able to determine how much the velocity has changed over the given period. For example, if a car takes 5 seconds to increase its velocity from 15 meters per second to 35 meters per second, then 15 meters per second is the initial velocity and 35 meters per second is the final velocity. To calculate the car's acceleration, we would first determine the change in velocity, which is 35 minus 15, giving us 20 meters per second. We then divide this change in velocity by the time taken, which is 5 seconds. This results in an acceleration of 4 meters per second squared. Since acceleration is a vector quantity similar to velocity, it not only has a magnitude or size but also a direction. Because of this vector nature, acceleration can be negative, which means the object is slowing down a situation, often referred to as deceleration. It is also important to note that the 4 meters per second squared we calculated represents the average acceleration that occurred over the 5-second time span. This is because in real-world situations it is rare for an object to accelerate at a perfectly consistent rate. The actual acceleration may have been higher at the beginning and then decreased over time, or vice versa. For example, the car might have increased its speed significantly during the first couple of seconds and then gradually reduced the rate of acceleration during the remaining few seconds. However, if the car had maintained a steady rate of acceleration for the entire time, then we would call this uniform or constant acceleration. Now we turn to the second equation for acceleration, which is slightly more complex and involves the concept of distance. In this formula, the letter S stands for distance, which is measured in meters. When we compare this equation to the first one we used, we see that the major difference is that this one incorporates distance instead of time. This means you will need to choose between the two formulas based on the information provided in the question. If the problem gives you distance, you will use this second equation, but if time is provided, then the original formula is the correct one to apply. In both scenarios, it is useful to keep in mind that if an object starts from rest or from a stationary position, then its initial velocity is 0 because it is not moving at the start. To explore this with an example, imagine a ball is dropped from a certain height above the ground, and we are told that just before it hits the ground, its speed is 7 meters per second. We are asked to calculate the height from which it was dropped, and we are instructed to ignore the effects of air resistance for simplicity. Initially, this might appear to be an impossible task because the only information given is the final velocity of the ball, which is 7 meters per second. However, since the ball was dropped and not thrown, we can safely assume that it began from a stationary position, meaning its initial velocity was 0 meters per second. Furthermore, because the object is falling freely due to gravity, we know that it accelerates downward at 9.8 meters per second squared, which is the standard gravitational acceleration on Earth. We now know the final velocity, the initial velocity, and the acceleration, and we want to find the distance, which is represented by the letter S. To do this, we must rearrange the second acceleration equation by dividing both sides of the equation by 2 times the acceleration. After rearranging, we simply substitute our known values into the formula. So we take the final velocity, which is 7, and square it, giving us 49, then subtract the square of the initial velocity, which is 0. We then divide 49 by 2 times 9.8, which is 19.6. This calculation gives us a result of 2.5. Therefore, the ball must have been dropped from a height of approximately 2.5 meters above the ground. That brings us to the end of this explanation. Hopefully, the principles of acceleration are now much clearer, and you have a stronger grasp of how to apply these equations in different scenarios. If you found this video helpful, please consider liking and subscribing to the channel, and we will see you again in the next session.